Alright, welcome. In this video we're going to be talking about some other polynomial theorems. Okay, last time we talked about the fundamental theorem of algebra, which told us that the degree of a polynomial and its number of zeros were intrinsically linked. And today we're going to talk about the complex conjugates theorem and Descartes' rule of signs. I think though in this video I'm going to only be talking about the complex conjugates theorem, and I'll save Descartes' rule of signs for a separate video to keep them both pretty short. But before I tell you the actual statement of the complex conjugates theorem, I think I want to just kind of work through a little example and show that we've already been seeing evidence of this, in the past few times. So, and even all the way back to the quadratic formula, we've seen evidence of this. So, if I'm going to try to find the zeros of this, okay, I'm going to start always by trying to factor. But it doesn't look good. I don't see a greatest common factor. I see more than 4 terms, so it's like, okay, we're not going to be able to factor this thing. So we're going to have to use the rational root theorem. It's like, oh man, I don't like that either, because 18's got a lot of factors and we would have to try those and they're negatives. At least there's no other leading coefficient. So, all right, let's just buckle up. We'll try 1, right? We always try 1 in this class and it usually works out for us. So I'm going to set up for synthetic division, x to the 4 minus 3x to the 3 plus 11x to the 2 minus 27x plus 18. I'm going to copy in the coefficients. And I'm going to try plugging in x equals 1, because why not? I know 1's going to work, right? I've delivered this lesson twice already. I know that 1's going to be a good guess for me. Okay, so 1 times 1 is 1. Add these down, multiply, add, multiply, add, multiply, add, and I get 0. And it's like, oh, okay, great. A little bit of the way on the way there. So this means I've got x minus 1 from here, because I divided away an x minus 1 and it divided cleanly. What I was left with was 1x to the 3, negative 2x to the 2, 9x to the 1, and negative 18, and no remainder. So I've got 1x cubed minus 2x squared plus 9x minus 18. And if I'm interested in the roots of this polynomial, that's where the polynomial is equal to 0. But wait a second, I'm looking at this, and now this is 4 terms, kind of a parallel ratio. 1 to negative 2 is the same as 9 to negative 18. I can factor this. And so I pull the things I can pull out of the first 2 and the second 2 terms. And then I factor out that x minus 2, and I've got all of my factors. This is as far as I can go. Okay, this is going to help me find my 4 zeros that go with my 4th degree polynomial. All right, so this thing could equal 0 if x was equal to 1. Okay, this factor could equal 0 if x was equal to 2. Okay, x squared minus 9, or x squared plus 9 could equal 0, but maybe you don't have enough experience solving this quite yet to where you can just see what the factor or what the roots are going to be. So I might just go, okay, x squared plus 9 equals 0. That gives me x squared equals negative 9. Take the square root of both sides. Don't forget the plus minus. The square root of negative 9, that's going to be 3i. Okay, so I've got plus or minus 3i. Okay, so here that's going to give me x equals 3i and x equals negative 3i. Okay, so these are my roots. Okay, and as far as the sketch of the polynomial goes, okay, we don't really have all that much to go off of if we're not going to use technology. But kind of the whole point of making a sketch is because we don't have access to technology. We know our zeros are going to be at x equals 1 and x equals 2. We've got a 4th degree polynomial with a positive leading coefficient, so we know both the arms are going to go up. The end behavior on both sides is going to be going towards positive infinity in the y direction. And we don't really know if there's going to be like some sort of like turning around or anything. We looked in my class this morning and we found that it actually doesn't. It's not as symmetrical as a parabola, but in other ways it does look very much like a parabola. Okay, so that would be a sketch of the graph. Okay. Really the thing I wanted to point out here was that we had some complex roots. There was 2 of them. Okay, and they come in pairs. Okay, they come in conjugate pairs. Is what I'm about to tell you. And 3i and negative 3i, those are complex conjugates, 0 plus 3i, 0 minus 3i. We've seen already solving quadratics with a quadratic formula that come back with imaginary roots. Those also come in conjugate pairs because it's plus or minus the square root. That square root's where the I comes in. So we've seen evidence of this before, so let me just tell you the actual theorem. Okay, so the complex conjugates theorem says that if you've got a polynomial that has real coefficients, and you've got one complex root that you know of, you've got another one as well. So if a plus bi is a root of a polynomial with real coefficients, then x equals a minus bi has to also be a root of that same polynomial. So I'm going to just work a quick example for you. All right, so we're going to find one of those minimal polynomial problems. So we're going to find a standard form polynomial of minimal degree with rational coefficients. I'll have more to say about that in a second. That has roots at x equals 1, x equals negative 2, and x equals 3i. Okay, so you remember how in the last unit we had a very similar theorem that was like, hey, if you've got a polynomial with rational coefficients, then a plus the square root of b is a root, then a minus the square root of b also has to be a root. Okay, rational numbers are a subset of the real numbers. So, rational coefficients is a little bit more strict of a condition than real coefficients, and so that's probably what you'll see in the instructions on these problems. Because you'll see in the next example, I'll be mixing in that theorem from the last unit with the complex conjugates theorem, and so we'll be having like square roots and imaginary numbers together, and we'll work with those. Okay, but on this one, I think I'm going to just kind of like dive in and show you how to work this type of problem. All right, so we learned quite a while ago at this point the connection between the factors of a polynomial and the roots of the polynomial. So I know that my polynomial is eventually going to be y is equal to some number a times x minus 1 times x minus negative 2 times x minus 3i. Okay, now, based on this theorem, if x equals 0 plus 3i is a root of our polynomial, then that means that x equals negative 3i, 0 minus 3i, that's also got to be a root. So I'm going to have over here x minus negative 3i. And then I'm going to just start to, distribute this stuff out. And, when I write this, a is what I would call the leading coefficient. And if they don't say anything about the leading coefficient, in the statement of the problem, we're just going to assume it's 1, right? Okay, so I'm going to go in here, and I'm just going to assume that we're talking about a is equal to 1. I might multiply these two together. So I'm kind of unfactoring, so I would add these numbers, right? Positive 2x minus 1x is positive x. Negative 1 times negative 2 is minus 2. And then these two, okay, I think I might bring a post-it note up. Okay, and if I took x minus 3i and multiplied it by x plus 3i, maybe you already know how this is going to go, and feel free to skip forward 20 seconds, right? But if you don't see how this is going to play out, we're going to do FOIL, right? First 2 is going to be x squared. Outside 2 is plus 3ix. Inside 2 is minus 3ix. And the last 2 is minus 9 multiplied by I squared. Okay, so what we're going to need to do is we're going to need to cancel off these middle terms, right, because they're the same except one's negative. And we're going to replace I squared with negative 1. Okay, so negative 9 times negative 1, that would be positive 9. And that's going to give me x squared plus 9. Okay, so that's going to be my factor right there. It's x squared plus 9. And I think I may have thrown that away a little too hastily, because I could probably use some real estate from this multiplication that I'm going to have to do. I'm thinking it's bigger than FOIL. I probably ought to just use a box. And I know that y'all have had a lot of success using the box method in my class this year, so I'm thinking, box method. Okay, I'm going to just fill out the box, because I know y'all know how to do that. And now I'm just going to combine like terms, right? I'm going to say y is equal to 1x to the 4. X to the thirds, I only have one of them. Okay, so plus x to the third. X squared, I've got positive 9 minus 2. X's, I've got 9x and then minus 18. So plus 9x minus 18. All right, should be enough. And that's going to be our minimal polynomial that has rational coefficients and roots at x equals 1, x equals -2, and x equals 3i. It just happened to be that in order to get them back around to having rational coefficients, we needed x equals -3i to be a root as well. All right, now the last example I've got for you is write an equation for a polynomial of minimal degree with rational coefficients that has roots at x equals the square root of 2 and x equals 4 plus 5 and has a leading coefficient -3. Okay, now it just says an equation, it didn't say standard form. So I'm going to leave this one in factored form. Okay? And I think it's probably good that you're aware that you have the ability to do both, right? That you start with factored form and then you expand it to get to standard form. Sometimes I might occasionally just ask you to leave it in factored form just for the sake of time, right? I don't need you to just be multiplying everything out always. I know you're decent at that, and I'll have you do it some to continue practicing and get even better at it. But for now, we're really talking about the roots, so I'm just gonna take this one. I might put it in standard form at the end of the video, but that'll just be real quick. So, okay, I'm going to have y equals some number times x minus the square root of 2. Now, if I know that x equals square root of 2 is a root of a polynomial with rational coefficients, in the last unit we learned that that means that x equals the negative square root of 2 needs to also be a root. So x minus the negative square root of 2. Okay. Over here, x equals 4 plus I. Okay, so I like to kind of just put brackets around this to remind myself that I need to distribute and kind of be careful with the negative sign. And then x minus 4 minus I. Now, the leading coefficient is -3. That's where the leading coefficient is going to go, right there. So let me just make that change. And that's an equation for a polynomial of minimal degree. It's going to have rational coefficients, and it will have roots at x equals square root 2 and x equals 4 plus I. Okay. If I don't ask for standard form, don't feel like you have to give it to me. I'll usually ask for standard form, but sometimes I'll ask for factored form, and don't make the mistake of doing more work than you have to. Okay, I'm thinking if you want to practice, because it will be really good practice, and there's going to be homework problems like this, distributing these out, okay, and actually multiplying them out, then you should probably pause the video here in a couple of seconds and just check your working. It's fine, because I'm going to bring the answers up here in like 5 to 10 seconds. All right, there you have it, standard form. Okay, so you see there was quite a bit more work involved after going from this, which I would call factored form, all the way down to here. We needed to distribute the negative over the 4 plus I, so I had x minus 4 minus I, and then distribute over the 4 and the negative I, so you have x minus 4 plus I, and then distribute all that out. Then you get to more multiplication here, okay? And then we distributed in the leading coefficients. That was kind of a lot. I didn't think you needed to watch me do that. Okay, that's going to be all for this video. Thanks for watching.